5 steps for sketching a curve. First one, we want to find the derivative. So find the first derivative, find the second derivative, because we're going to use those algebraically. Second step is we're going to set the first derivative equal to 0 to find all the stationary points. Right? That is when the slope is flat. Okay, we will find the stationary points. We won't necessarily know the nature when we're doing it algebraically. Okay, we'll determine the coordinates, and then we will verify the nature using the second derivative test. The fourth thing we will do is we will find the points of inflection by setting the second derivative equal to 0. Now remember, the purpose of this is to determine concavity of the function. And one nice way to think of it is when the function is at its steepest. Okay, that's one of the possible outcomes for finding a point of inflection. Okay, our fifth step, once we've found that, will be to verify the concavity. This question is pretty much saying sketch a function, clearly label all stationary points and all points of inflection. So it's a curve sketching question. I'm just going to follow my 5-step guide. So first one is find some derivatives. Great, second step, I'm going to find the stationary points. For that, I need to use the first derivative. Great, so I've found stationary points there. Before moving on to step number 3, I just want to determine the coordinates, okay, just because I like to keep my work organized as I'm doing this, especially tech-free. So I'm going to sub these values into the function, okay, this function up here. Okay, so I'm going to sub. So I found my derivatives, I found my stationary points, I set them equal to 0, and I found the coordinates of those stationary points. I don't know if they're maximums, if they're minimums, if they're points of inflections. So I'm going to use the second derivative to verify their nature. Found out that our first one here was a minimum. Great. So this is a minimum. Cool. The second one, I don't know what it is. I cannot say it's a point of inflection, okay, because I need to verify points of inflection. So I can see that that is going to be one of my solutions here. So my fourth step is find the possible points of inflection, or the ones that I can verify. So find point of inflection, that is by letting f double prime of x equal to 0, but I will need to verify those points of inflection. Okay, so I get x equals 3, x equals 1. They are the possibilities for my points of inflection, but I need to verify this. Okay, so I need to check the concavity around these points. Okay, so my step number 5 is to verify. Okay, so I've got a couple of points here. I need to check for 1 and for 3. Okay, I know there's going to be no concavity there, so I'm just going to put nil. All right, and I'm going to check a point to the left and to the right of each. So 0 would be to the left, 2 is to the right, and then if I suss out for 3, if I just zoom up here, I know 2 is to the 3 of right, so that's why I don't need to put in an additional point here, and I'll put in 4, and I'm just checking the concavity. So I'm going to substitute these values into the second derivative, which I'll remind myself the second derivative is equal to, yes, that is the second derivative. So I'm going to sub those in, and I need to make sure that I've got downward concavity, then upward concavity to have a point of inflection. Okay, even if it is a horizontal point of inflection, okay, which at least for x equals 3, I'd imagine, you know, I'm suspecting it is. Okay, but even then, we've got to check that it's got, even if it was a horizontal point of inflection here, we've got to have, for example, we've got to have some downward concavity, because that would suggest that the slope's decreasing, it goes flat, but rather than continuing to decrease, so if we had downward concavity, then downward concavity, that would be a maximum. Okay, but that's not what happened. Okay, so what we would need to get for it to be a point of inflection is downward concavity and then upward concavity. Okay, and so even if it was a cubic, that's exactly what a cubic does. Okay, it's got downward concavity and then upward concavity. Okay, but we verify it's got to be either side, up and down, and we verify using the second derivative. Okay, so we've verified that both are in fact points of inflection. Okay, which is very nice. Now we'll need to sketch this function. Alright, I've lazily not found, and you can see why you need to find the coordinates as you go, because if you get to this stage and you've run out of, you don't want to do that. So this coordinate was 331. I need to sub f equals 1 into the original function, okay, which was f of 1 was equal to, what was the original function? Okay, and that'll give us that coordinate, so 1 at 1, 15. Alright, now I've got to try and piece all of this together. Okay, so at least this graph here, I knew that this was a minimum point here, so that should go up like so. This was the point of inflection, so it should flick around at that point. This had a flat slope, and it was a point of inflection, and then it concaved up from there. So this is what it looks like here. We'd have y equals x to the power of 4 minus 8x cubed plus 18x squared plus 4. Right, and so just so we can verify some stuff with our concavity table here, right, we had at x equals 0, it was concave up, and at x equals 1, it was a point of inflection. So this here, this is all concave up. And if we go over it in a different color here, we can see that just that pink section there, that's concave up. Okay, that's a cave or like a skate ramp that's, concaving up. And then we go between 1 and 3, okay, we had downward concavity. So between here and here, right, and we would, if this green line continued, we would in fact have downward concavity. Okay, if it continued, we'd have a concave down, but it doesn't continue because it gets to that point where we have got a flat slope, and I might do this in a light blue here, a flat slope there, and there was a minimum point here, so flat slope there, and then it began to concave up again, concave up after that point there, and it continues to concave up because there's no other stationary points. Okay, so we had and so that's concave up. Okay, so hopefully this is helpful.